Hello and good afternoon, everybody, on this 30th of April 2020. So today we will start with a new chapter, and that is entitled Magmatism within Plates, and that is chapter 9. So magmatism within plates, and therefore we will just start with the first separation, or with the first part of it. That is then the magmatism within the oceanic plates, yeah? So, and these are then the oceanic islands. So here we have a nice overview map over the distribution of volcanic islands within the Atlantic Basin. So in this shaded field, that marks just the location of the middle ocean ridge, the middle where you can form the more basalts. So, and therefore we can now find a lot of oceanic plates. Yeah, we have here the Azores, for example. We have here Madeira. Then we have Canary Island, and we have the Cape Verde Islands. Yeah. So then we have here Fernando de Noronha. Then we have here Trinidad. Yeah. From Trinidad we can also get a lot of tobacco. So then we have here the Faroe Islands, very in the north. Yeah. So, and here we have then again the aseismic ridges, the Rio Grande Rift, and the Walvis Ridge. Yeah? And the Walvis Ridge is here located very close to Namibia. So, and there I just forgot, here we have the Colorado Seamount. Yeah, these are then all oceanic islands. So, but when we are talking about oceanic islands, then here in the middle we have a other very famous ocean islands located in the North Pacific, and that is the Hawaii chain, the Hawaii volcanic chain, yeah? So, and while we are talking about the Hawaii volcanic chain, here it is, yeah? So here on this map we have just the situation now in the Pacific, in the North Pacific, as well as in the South Pacific, yeah. Here we have the Imperial seamounts, and here we have then the Hawaiian Islands here, yeah. Can you see it here? There are the Hawaiian Islands, and you know the Hawaiian Islands, they are hotspot volcanoes, yeah. And there we are starting here with the Emperor seamounts here in the top, yeah. 75 million years ago. Then we have here a lot of volcanic eruptions along these lines between 75 million years and 40 million years back. And then we have here midway 25 million years, and then we have here now the Hawaiian Islands, and they are still active. At least one is still active, yeah? So then here we have another group. We have the Austral group here. And here we have the Tuamotu group, yeah? So, and therefore we have here we have the active McDonald's seamount, yeah? Has nothing to do with the McDonald's fast food chain, yeah? That is just the seamount there. And this seamount was already there before the first McDonald's restaurant opened in US. So, and here we have then the Pitcairn Islands, yeah? So now we are going just to the next spot, or next slide. So, and here we have just a roughly a sketch map which shows us just roughly how such a hotspot chain works, yeah. You know, I mean, the ocean we have here at the top, that is the lithosphere from the oceanic crust, and the lithosphere from the oceanic crust is moving, yeah? So because all the lithospheric plates, it does not matter if we are talking about continental crust or oceanic crust, they are moving, yeah? We have here then the plate motion, yeah? That is the plate motion, the direction of the movement. So, and here in the asthenosphere we have a hotspot sitting, and such a hotspot we are calling a plume, yeah? You know this by now. That is a plume. So, and this plume is then just melting, or the melt from the plume is just melting through the lithosphere and forming at the top of the lithosphere a volcano, yeah? And this is then an active volcano, yeah? So, and these volcanoes here, more to the left, they are extinct volcanoes. They are not longer active because due to the movement of the plate above, yeah, then we are removing the volcano from the active plume below, and therefore these then are extinct volcanoes, and we have there an increasing erosion of the volcanic structure. Yeah, you know this now. I mean, you should actually know this from the first year class. I mean, that is how atolls are forming. Yeah, you know, atolls actually very nice places to go there for swimming and snorkeling. Yeah, but such an atoll is actually just the rotten part of a volcano. Yeah, so and therefore they are forming just these circles, and then they are disappearing. And a lot of people they have nowadays a huge issue with their islands, yeah, because like Kiribati, because they are disappearing, you know, and then they are coming up with climate change and so on, which is actually all true. But the problem is, due to the erosion of the base and due to the deposition of all these sediments above, yeah, from such an atoll, it will just suck together, and then they will disappear earlier or later with climate change and also without climate change. That is just a life cycle from such an from at first, from the beginning, from an active volcano. Then this active volcano becomes more and more, it becomes extinct, then it becomes more and more eroded, and then they are disappearing beneath the surface, yeah? So here we have then the distribution of hotspots within the oceanic and continental plates as well, yeah. So I mean, at the oceanic plate we have here the world famous Hawaiian hotspots, yeah. So, and here you have some other hotspots everywhere around in the oceanic crust. There are quite a lot of hotspots around, yeah. Also here in the North Atlantic plate we have some hotspots. So, but we have also a lot of hotspots on the continental side, yeah. So, in this we will talk about the hotspots and or the basalts on the within the continental plates in our next chapter. But here you have just now the distribution from all the hotspots hanging around on this planet. So chemically, chemically the hotspots are also enriched, and therefore we need a plum component inside. We need a plum component inside, and that plum component, it comes then from the lower mantle in a depth of about 700 kilometers. We discussed this before, yeah. So, and this plum component from the enriched basalts, from the E-morb, yeah, that is enriched morb, and that comes, or we are thinking the reason for that this is enriched, that is due to all these subducted old fragments from oceanic lithosphere into the Oib reservoir, yeah, and here in the lower mantle we have the Oib reservoir, and there these slabs, they are becoming subducted, then they are hanging a while they are hanging a while at the boundary and at 670 kilometers around till a certain threshold is reached, and then they will break down in the lower mantle, and there they are becoming enriched, and then you have an OIP source reservoir. That is the model behind. And here we have then the situation just for a ridge-centered hotspot, yeah, that is here at the mid-ocean ridge, yeah. If we have there an OIP source inside, an enriched basalt, so and here we have the intraplate hotspot, and the intraplate hotspot, that is an ocean island basalt, and this is enriched compared to MORB, because we have there always the component from the lower mantle or from the OIP reservoir inside. So, and therefore we have a model which depicts a two-layer mantle in which the lower OIP source reservoir is composed of a mixture of near primordial mantle and recycled subducted oceanic crust. Yeah, that is just what I told you. Diappears upwell from the interface between the ocean island basalt reservoir and the overlying depleted asthenosphere. We have then the MORB source reservoir. So, and that is where the enriched component comes from. For the intraplate hotspot, here we have then the movement of the plate, yeah. We have the movement of the plate, and therefore you are getting a hotspot chain. And here we are forming, for example, a seamount, yeah. And here on that side we have the Iceland arc, yeah. So what have we here? We have the structure of the thermal plumb impinging on the base of a rigid 100 kilometer thick oceanic lithospheric plate. Yeah, here we have, and if we are talking about a 100 kilometer thick oceanic plate, that means that is already an old one, yeah? An old one, old plate, which has already cooled down quite a lot, yeah? So, and here we have then the movement that is shown by this arrow of the lithosphere above. So, and here we have at zero, we have the axis of the plumb. So, and then we have here the zone where we have where partial melting will take place. And here we have our isotherms. Yeah, here very close to the axis of the plumb. It is very hot. Here we are facing temperatures of 1500 degrees. Here even to very close to the axis 1600 degrees Celsius. And here at the bottom of the lithosphere, here we have of course the 1200, yeah. Because at the boundary between lithosphere and asthenosphere, that is a thermal boundary. I told you this before as well. And there we are having then dealing with temperatures always of about 1200 degrees Celsius. And here below we are dealing with temperatures where the partial melting takes place of about 1400 degrees Celsius. So here we have a schematic sketch map, how the Hawaiian Ridge look like. Here we have the Hawaiian Ridge, here is the sea level, yeah. Here at the top is the sea level, here we have the volcanic edifice, and here we have sediments, or sediments are infilling here. And these sediments are of volcanogenic origin. So then we have the pre-existing downwarped oceanic crust here. Here we have the seismic moho, yeah, that is the seismic moho. and here we have the volcanic plug and the rise up of the melt, and then we are forming here the Hawaiian Ridge. Yeah, in the Hawaiian Ridge is then near the islands of Oahu. So here we are feeding, I mean in a depth of 20 kilometers, we have the volcanic plug. Here we are feeding it. Here we have some crustal sill complex, yeah, or cumulate sequence. Then we have the rise up of melt and forming here the Hawaiian Ridge beneath the sea level, and if you are feeding it long enough, then it will pop out of the water, and then we have formed the next island. So now we have here a cross-section of the subvolcanic magma plumbing system beneath the Hawaiian volcano Kilauea. And Kilauea, that is now the youngest volcano, and that is the active one, yeah? So, and here we have the Kilauea caldera, and here the Kilauea Iki, and then we have here the summit reservoir, and here we have the east drift zone, here we have Mauna Ulu. So, and that is how it looks like in depth, or that is just the mantle. We have here the upper mantle, we have here the oceanic crust, and here above we have the volcanic shield, and we have the magma of the magma storage reservoir, yeah? So, and I mean these volcanoes, which are then just more far away, they are not longer fed by the magma storage reservoir, yeah? Because the plate above is moving. So, in the plate above, that is this part here, yeah? The oceanic crust above is moving, and if it is moving more and more away, then we are cutting just the magma reservoir beneath, yeah? Then we have the eruption will take place till it is empty, and then when we are waiting now another 20 million years or 8 million years, I don't know, then the oceanic crust above is moving maybe to that side, and this Kilauea is not longer active because it is now apart, or by then apart from the magmas from the reservoir in the upper mantle. So here we have a schematic Hager variation diagram to show the geochemical consequences of magma mixing as opposed to crystal fractionation. So here we have, for example, on the y-axis the iron total, yeah, iron 2 plus iron 3 plus. Here on the x-axis we have the SiO2 concentration. So, and here we have a basic magma, and this basic magma becomes then more and more acid, and here between we have the mixing line between the two magmas, yeah? So, I mean here above at the solid line we have the typical toleitic fractionation trend, you know. We can fractionate a basic or mafic magma so long till we are getting at the end an acid magma, yeah? You know this by now, yeah? Because the mafic magmas or basic magmas, it's the same, for are formed at the beginning and are stable at high temperatures, yeah? So, or not stable, I mean fractionation and crystallization processes will take place. We are removing from our mafic magma always more and more magnesium, yeah, and iron and calcium and so on to form then very at the beginning minerals like the olivine and the orthopyroxene and the clinopyroxene and the plagioclase, and therefore we are removing actually more magnesium compared to silica. Then our magma becomes then the residual magma, becomes then always more and more enriched in SiO2 and depleted in magnesium, and therefore you are changing the composition. You should know this by now. Or we can have just a mixing between the two magmas. Yeah, we have a basic magma and we have an acid magma, and then we are mixing them up. Yeah, a lot of things are possible here. Yeah. So and now we are making or we are splitting the tholeiitic magma basalts from the alkali basalts. So what are the main differences between tholeiitic and alkali basalts? So the first phenocrysts. So in the tholeiitic basalt we have infrequent large olivine phenocrysts, commonly unzoned, may show reaction reams of orthopyroxene. In an alkali basalt, we have medium-sized olivine phenocrysts common, often strongly zoned with more iron-rich rims. And the iron-rich rim, that is an indicator for the temperature, and we have iron-rich rims, then it means the magma cooled down quite much more compared to the tholeiitic magma. So then in the tholeiitic magma, orthopyroxene phenocrysts may occur. In the alkali basalts, orthopyroxenes are absent. So then why is this? I mean, because the tholeiitic basalts, they are formed at higher temperatures. So plagioclase phenocrysts often appear early in the crystallization sequence, because the calcium-rich plagioclase is formed also at high temperature. So plagioclase phenocrysts, less common, appear later in the crystallization sequence. That means these plagioclases then are more sodium-rich. Then we have in the tholeiitic basalts, we have olivine plagioclase orchide. We have less olivine, then we have the plagioclase, and we have more orchide inside. So, and I mean in the alkali basalts, the orchide is just staying as in the middle, and we have more plagioclase inside, yeah, because the plagioclase is picking up the sodium. So then we have in the tholeiitic basalts, we have phenocrysts of pale brown orchide, yeah. So and in the alkali basalts, we have titaniferous orchide phenocryst, strongly zoned with purplish brown rims. So then these are the things when we are looking at the phenocrysts inside. So then the ground mass in the tholeiitic basalt, the ground mass usually relatively fine-grained with an granular texture. No ground mass olivine. Ground mass pyroxene is available, subalkalic orchide or orchide plus minus pigeonite. No alkali feldspar or analcite in the ground mass. So then we are looking for the ground mass in the alkali basalts. Ground mass is relatively coarse-grained because it cools down much slower, and it cools down over a much more wide temperature range, yeah? So ranging from intergranular to ophitic. So then we have no ground mass in the olivine, then that is for the tholeiitic basalts, and we have in the alkali basalts, we have ground mass in the olivine. So in the tholeiitic basalts, we know no alkali feldspar or analcite in the ground mass. In the alkali basalts, we have interstitial alkali feldspar, and analcite may occur in the ground mass, yeah? So, and then in the tholeiitic basalts, we have interstitial glass, relatively common. That is also an effect of the fast cooling rate, yeah? and in the alkali basalt we do not have interstitial glass or rare or absent. So then associated rocks, I mean in the tholeiitic basalts, they are always associated with ultramafic xenolites, but this is very rare. Associated accumulate rocks are picrites, oceanites, rich in olivine phenocrysts. So associated accumulative rocks are ankaramites, rich in olivine and orchite phenocrysts. So then we have the pyroxene composition in Hawaiian tholeiitic and alkali basalts. So we have here in Hawaii, we can find tholeiites and we can find alkali basalts, and they can be separated from the different volcanoes. Yeah, some of the younger volcanoes are tholeiitic in composition, and the older ones are alkali. But we have to figure out this. Pyroxene compositions in the Hawaiian tholeiitic and alkali basalts. Yeah, so the pyroxenes are then also chemically different. In the M represent always the megacrysts, and G, that is the ground mass, and there both of them, both clinopyroxenes are different from each other. So then we have in the ground mass, we have also pigeonite inside, yeah, and the pigeonite, that is a high temperature calcium bearing orthopyroxene, and we have a normal megacrysts of orthopyroxene inside, yeah. Here to photomicrographs comparing the petrographic characteristic of the oceanic island tholeiites and alkali basalts. So A, we have then tholeiitic basalts from Hawaii, phenocrysts of olivine set in a fine-grained matrix of plagioclase. Clinopyroxene and glass. So that we have here, we have huge olivine and these small fine-grained plagioclase needles. So in the number B, we have an alkali basalts from the Azores, yeah, which contains glomeroporphyritic aggregates of titano-orchite, plagioclase, and magnetite. So here we have again this famous diagram. I showed you this at the beginning of the class as well. So we have then the SiO2 concentration on the x-axis and the Na2O plus K2O concentration on the y-axis. And we have the different dots and crosses inside. Yeah, here this axis here, that is the composition of Iceland. Yeah, so and there in Iceland you can find basalts, and we have basaltic andesites, dacite, and rhyolites. We have here the whole sequence from mafic to very acid. Yeah, it's actually very nice. So then we have here in black dots, that is the ascension. There we have here also basalts, basaltic andesites, but then we have trachy andesites, yeah, because here these rocks there are more alkaline. Then we are forming here the trachytes, and we are forming here also something close to rhyolites. So then in circles we have here the Tristan du Canha, we have here basanites and tephrites, phonolithic tephrites, and phonolites and trachytes. And here the star, that is the average of the tholeiitic basalts from Hawaii. So here we are forming beneath this black line, we are forming we have the subalkalic tholeiitic trend, and here above we have the alkalic trend. And if you are following the alkalic trend, of course, then we have more sodium and potassium inside, therefore alkalic, yeah. So here we have then Harker diagrams again, yeah, for the major elements we are using always the Harker diagrams. And here, as typical, we have the SiO2 concentration on the x-axis, and on the y-axis we have the potassium concentration, and now we are comparing the trends there. Yeah, here the stippled line that marks the subalkalic trend or the boundary between the subalkalic trend to the alkalic trend. Yeah, so here at the ascension we are lying very close to the alkalic to subalkalic trend. Some of them are subalkalic, yeah, but just at the boundary. Some others are alkalic, and the trend from them in average is alkalic, but very close to the subalkalic. If we are going to GAF, yeah, we are starting here with a basaltic composition, but the trend is really alkalic. The same for St. Helena, yeah, we are starting also in the composition with basalts and following then the alkalic trend. Same thing for the Azores. At the Tristan de Cunha, it is, of course, it is totally alkalic. And if you are going to Iceland, we are following very nicely a subalkalic tholeiitic trend. Yeah. So, and I mean, Iceland is sitting on the Middle Ocean Ridge, and the Middle Ocean Ridge basalts, they are already by definition tholeiitic. So now we have this nice diagram here. We have also again the boundary between alkalic and tholeiitic. So when we are following the tholeiitic trend, we are following more or less the fractional crystallization trend. That is this here, yeah? So, and if we have the alkalic trend, then we are going here more decreasing degree of partial melting, yeah? And we have here the different locations. So we have here now the Hawaiian Islands. Yeah, we have Mauna Leo, Kilauea, Mauna Kea, Hualalai, and Kohala. So, and then we can see that the older ones, Kohala, Hualalai, Mauna Kea, they are following more the fractionational trend. So whereas we have Kohala, they have also a lot of alkalic trends, yeah. So and now we are looking for the recent one, that is Kilauea, and there we have the crosses. and Kilauea is the youngest one, and that is toluitic one, and that follows the fractional crystallization. So now next diagram, we have the variation of weight percent in Al2O3, titanium oxide and magnesium oxide versus SiO2. We are starting here always with a mineral assemblage consists of olivine, CPX plus magnetite. So then we have olivine plus CPX plus magnetite, and the plagioclase comes in at this point, and then the Al2O3 concentration becomes less in our residual belt because it becomes Al2O3 is picked up by the plagioclase. So here we have then olivine, CPX and magnetite. And there we have at first a strong decrease in titanium oxide, and then it becomes then more or less. So when the titanium oxide is then picked up by the magnetite. Not really too much. So, but here we have now the magnesium concentration, and the magnesium concentration is mainly picked up by the olivine here, yeah. So, and then the magnesium concentration becomes less in your melt, less, and the SiO2 concentration becomes relatively to that enriched, yeah, because if you are looking for the mineral chemical formula of olivine is Mg2SiO4. You are removing 2 magnesium but only 1 silica. That means your residual melt becomes relatively more enriched in silica because you are removing less, but you are removing always 2 moles of magnesium, yeah? Should be so far clear. So then we have here the next Hager diagrams. We have here the variation again on the x-axis SiO2. So we have here at the beginning a very vertical line. Then the plagioclase comes in. Plagioclase is picking up the aluminium, and then our melt becomes then depleted or more depleted in aluminium, yeah. Or you are coming from the other side, yeah. So here we are starting here. We have the olivine, the formation of olivine. We are taking all the magnesium from the melt. So, and therefore our melt becomes then more silica enriched. Whereas when you are taking the aluminium, the silica concentration goes also down, because if you are looking for the anortite, that is CaAl2Si2O8. So, and when we are removing 2 aluminium, we are removing also 2 silica, and therefore it goes down. So here the same for the titanium. The magnetite comes in, and the titanium becomes removed from the system, but there is no silica inside. So, and therefore the silica becomes relatively enriched. The same here for the apatite. We are removing the phosphate, and if you are looking at the mineral chemical formula of apatite, then you will see there is no silica in. You are removing the phosphate, and therefore the residual melt becomes then enriched in silica, more enriched, yeah, because silica is still in the melt. So, and these are just some or a few examples what happens through fractional crystallization. So in the same thing here, we have the barium. The barium is also sitting in the plagioclase, so but just as a trace element, but here barium is just listed as trace element. Strontium is also as a trace element in plagioclase, so and then it goes down. So and now here we are comparing selected trace elements abundances in middle ocean ridge basalts, oceanic island tollites and oceanic island alkali basalts from different locations. So we have here the potassium concentration at the middle ocean ridge basalt ranging between 0.1 and 0.3 weight percent. Then we have those ones from the ocean island tollites that is ranging between 0.2 and 1.2 weight percent of potassium. Yeah, therefore we have then more potassium inside. And then we have the ocean island alkali basalts, yeah, where we are dealing then with partial melting, and there we have then much more. We have a potassium oxide concentration inside of ranging between 1 and 7% weight percent. Barium the same, very low values at the middle ocean ridge basalts. Ocean island tollites have more, but much more we can find in the ocean island alkali basalts. So the same for the strontium, same for rubidium, same for zircons, same for niob, and the potassium to barium ratio is then also very different from the basalts from all three locations or from all the three basalts. So then we have here another nice diagram. We have here a p-type morb, yeah, P, and then we have a moment. We have here the big barrow that is the shows us the zircon neodymium ratios in n-type morb, yeah. So and here the P, that is the plum morb, the zircon neob ratio in plum morb, and then T, that is in the transitional zone, yeah. And here we have the yttrium to neob ratios in the n-type morb, then in the transitional zone, and here beneath in the p-type morb, that means the enriched plum morb, yeah. So and here we have then the variation from the southern middle ocean Atlantic ridge, yeah, that is here MAR. Then we have those ones from sphere, that is morb from the southwest Indian ridge. Then we have the trend for AAR, that is morb from the American Antarctica ridge, yeah, Antarctic ridge. We have the triangle, that is the average Tristan, and we have the star, that is the average Bouvet basalt, yeah, that is this here. So and then you can see here we have there very nice trends. So in these data points, they are just representing the one from the middle ocean ridge in the southern part of the middle ocean ridge, middle Atlantic Ocean ridge. Then here we have the variation of neob zircon ratio with latitude in morb erupted along the southern mid-Atlantic ridge. from different locations. So here we have the Ascension, the St. Helena, and the Tristan da Cunha, and the Gulf, yeah. And here we have the latitude, yeah. So and now we can compare how Neop and the Neop-Circon ratio varies with the latitude, yeah. So and that is just erupted along the southern mid-ridge from 0 to 48 south, degrees south. So then these two nice diagrams, we have the nickel and chromium constant variation diagram for nickel and chromium content versus magnesium oxide for the basalts from the Gulf Island, yeah. And here you have also very nice trends in nickel, and here you have very nice trends in magnesium. So when we have here with increasing magnesium, the nickel concentration also increases. What is this for? What is the sign for this? That is just that we have an increasing fractionation of olivine. Yeah, we have then more olivine in our bulk. And the same for a trend for the chromium with increasing magnesium. We have also increasing chromium. And this chromium is actually located in the spinel, which we are calling chromite. So maybe this data are typical for a basalt which is formed at very high temperatures. So then we have here the next spider diagrams. So we have here the Kilauea trend, Kilauea tolite, yeah. Then we have here the Mauna Loa tolite, yeah, here in circles. Then we in red in this open squares we have the Kohala alkali basalt, and then the dark filled squares, they are the Azores alkali basalts, yeah. So and this here is just the N-type morph, and then you can see that all of, and here we have the P-type morph, that is the enriched component inside, and that there you can see that is melts which are forming the ocean island basalts are more related, or actually related, to the trend of the P-type morph, and that means the plum component from the lower mantle, yeah. And you can also see that the toleites are not necessarily enriched, but the Kilauea toleites, they are very enriched, yeah. So then we have here the oceanic island alkali basalts. Here A, we have the oceanic island toleitic basalts, yeah. And here we have the, now it is okay, yeah. And here we have then the oceanic island alkali basalts. So in the alkali basalts, they are even more enriched, yeah. When we are normalizing our rock samples with the chondrite, they are even more enriched, especially in light rare earth elements, because light rare earth elements are very mobile in the fluid and in the gas phase, yeah, and that we will discuss then also later. So here we have the next spider diagram, rock to primordial mantle normalized. Then we have here the N-morp, the P-morp, and the toliitic basalt. So, and here to compare to that, we have then here the alkali basalt, the pattern for the alkali basalt, and here above we have the pattern for the nepheline melilith, which is actually a very silica undersaturated basalt, or melilith, yeah, melilith is silica undersaturated. So that is then formed in a very, very late residual melt, yeah. So, and therefore it is very enriched on incompatible elements. So incompatible elements, abundances, normalized to primordial mantle values for typical toliitic and alkali basalts and the melilith nephelinite from Hawaii. Yeah. So here we have then the toliitic basalt, which is a product of fractionation. So then the alkali basalt is already more enriched, whereas the toliitic basalt is following more or less the pattern from the enriched morp, yeah, from the P morp. So in the nepheline melilith, it is then formed in a very, very late stage, and that is then very enriched in incompatible elements. So now the next thing what we are always doing, that is we are looking at the isotopes. At the x-axis we have everywhere the 87 strontium to 86 strontium isotopes, and on the y-axis we have the 143 neodymium to 144 neodymium. So, and then Dm, that is the depleted mantle, yeah. We have here just the key. MAR, that is this field here, that is our Middle Ocean ridge. Then I, that is this here, that is the Iceland. AS is Ascension. Then C is Canars. SH is St. Helena. B is Bouvet. A here, that is the Azores, showing a very wide field. Then we have here WR, that is the Walvis Ridge, just here very close to Namibia. So then we have the major components identified. That is the depleted mantle, yeah. SHC, that is the St. Helena component. And EM, that is the enriched mantle, and the enriched mantle is just lying on the bulk earth, yeah, that is the average earth, the bulk earth. So going now in this direction, then we are coming close to the isotopical composition from the oceanic sediments. So, and this is the distribution from all these components in the Atlantic, yeah, in the Atlantic Ocean. So now we are going to the Pacific Ocean, and in the Pacific Ocean we have then other hotspots or ocean island basalts. We have here the felt S. S is Samoa, that is in the South Pacific. SO is the Society Islands. M here, that is Marquesas. Then TU, that is Tubai. That is here. And so on, yeah. GL, that is Galapagos. You know Galapagos, that is there where the huge turtles are at home, and then. So, and then we have here, that's the same for the Indian Ocean, Again, with the depleted mantle inside, with the St. Helena component inside and the enriched mantle plots inside. So, and then we have here always the morph, yeah, in this dark, we have here the Eastern Pacific rise, that is there the Middle Ocean ridge, yeah, and the Middle Ocean ridges are everywhere plotting in the same thing, but the Middle Ocean ridges in the Indian Ocean, they are showing a just more wide isotopical composition, yeah. So, and therefore you can then use these diagrams again to classify geochemically where your rocks are come from, or to what they are belong, or what are the geochemical characteristics of your studied rocks. (143 here again the 87 strontium to 86 strontium, and the 143 neodymium to 144 neodymium. We have here the bulk earth, that is here the cross. So, and then we have here some dots inside, and these are lersolite xenolites from the subcontinental lithosphere, yeah. The subcontinental lithosphere, please be always aware of the subcontinental lithosphere, yeah. So, and there we have these black dots inside. And for a comparison, we are showing the oceanic basalt array. The oceanic basalt array, here we have the morph, yeah, and here we have the ocean island basalts. So, and here we have the plot from the lersolites from the subcontinental lithosphere, and they are correlating actually very well, or some of them, with the Middle Ocean ridge basalt, yeah, and also with the OIP. How does this connection take place? That is just because these lersolites are the residuums of the basalts, and when they are a residuum of the basalt, of a Middle Ocean, of a morph or something like this, then they are geochemically very close to them. That's all, yeah, of course, I mean. So, and the same for the ocean island basalts, for those lersolites plotting inside this field here. Yep. So then number A, we have the Atlantic Ocean here again. So, and here we have again the depleted mantle, the enriched mantle, and the South Helena component. But we are using now on the x-axis the 206 lead to 204 lead, and on the y-axis the 207 to 204 lead. So, and then we have here in the key, we have number D, that is the Discovery Seamount, then CV, that is Cape Verde Islands, FN, that is the Fernando de Noronha, and NHRL, that is the Northern Hemisphere reference, yeah. So, and therefore we have now our different fields. Here we have in the gray field the Middle Ocean ridge. Going then to a higher, is 207 lead to 204 lead in the Pacific, then we are getting the composition of the sediments, yeah. Here again another diagram plotting 206 lead to 204 lead against 206 lead to 204 lead. And here again inside the depleted mantle, the enriched mantle, and the St. Helena component. And different dots, which are representative measurements from certain locations. Here we have AM, stands here for Amsterdam. Then we have RE, that is Réunion. That the Réunion we will discuss also later something about Réunion. Yeah, that is also important because there is a relationship between Réunion and the Deccan Trap. Then we have R, that is Rarotonga, that is here. Then we have Mauritius, that is MO. And MO we have here next to Réunion. Yeah, these are two islands lying in the Indian Ocean. Then we have CO, that is the Comores, that is here. MPE, that is the Marian Prince Edward, yeah. The Marian Prince Edward, that is here, this large field, I think so. Then SP, that is St. Paul. No, this grayish field, that is the Atlantic Pacific Morb, and this grayish field, that is the Indian Morb, yeah, and they are lying here on this array, and then the array, that is the NHRL, and that we have discussed before, what the NHRL is. No, and they are all here. They are very related to lying. These ones they are plotting then on the array of the Atlantic Pacific Morb, yeah, and they are lying between the depleted mantle and the St. Helena component. So, and these ones here from the these ones here within the stroke line, within the stippled line, they are more close to the enriched mantle. So what do we have here? We have figure A and we have figure B. And there we can see the world map showing the distribution of global isotopic anomalies for Morb and OIP, yeah? The contours shown are subjective, as there are many areas for which isotopic data are lacking, yeah? So there is still this thing for getting on the whole and always a more and more detailed picture from everything. Then we should have a very constant and a very solid database, but often we are still lacking on a good data set, and therefore a lot of things are often interpolated. So therefore this figure is not that important for us. So here we have the detailed map for the delta 8 through 4 anomaly for Morb and OIP from the South Atlantic and the Indian Ocean. So that is then again, here we have the South Atlantic here, yeah, here Wolf is rich again, the Rio Grande rise, which we will discuss also later in detail about things about the Rio Grande rise. And here we have the Carlsberg Ridge, and here we are going into the southern part of the Indian Ocean. So, and here we have then the distribution here we have the zone of maximum Dupal anomaly, that is the geochemical anomaly from before, and here we have the aseismic ridges, and here the Walvis Bay is an aseismic ridge, the Rio Grande is an aseismic ridge, and then we have here the Naineti East Ridge is also an aseismic ridge, yeah. And here in this shaded zone, yeah, we have here the Dubai anomaly, yeah. There we have our geochemical anomaly. So, and now comparing this with the basalts here in small blue dots, we have here everywhere morb, yeah, where we have here on the 10 is morb. Then here along this Carlsberg Ridge and here along, everywhere along in the South Indian Ridge, we have here everywhere morb, and then the small black dot with the circle around, there we have then the ocean island basalt, like here in St. Helena, in Trinidad, in Ascension, the Fernando de Ronda is morb, and here San Paulo is north, and Cape Verde here is also OIB, that is ocean island basalt, and that means they are enriched. Yes, then we have here Réunion and Mauritius again. Réunion, I told you, we will discuss this later on also more in detail, because there I have a good example. Then we have here the Comores are ocean island basalts. So, and they are all actually more or less away from the middle ocean ridges. And there we have then everywhere a component from the lower mantle inside, and this component is added through old remnants from a subducting slab, and such an old subducting slab or a part of such an old slab can hang around there in the Earth's mantle for 2 billion years or up to 3 billion years. So, and within our zone of maxima of our geochemical anomaly, we have then a lot of ocean island basalts inside, yeah? So here we have again a comparison between rocks from the Atlantic Ocean, the Pacific Ocean, and the Indian Ocean. So, and the author is using here the 206 to 204 lead isotopes, plotting against the 87 strontium to the 86 strontium. And she, that is actually the author of this book is a she, that is Marjorie Wilson, yeah. We have here the depleted mantle, the enriched mantle, and the St. Helena component. And we have here the different blocks. Here, when we are increasing the 87 to 86 strontium ratios, then we are adding maybe sediments. Yeah, we have discussed this before as well, the addition of sediments. And then we have in here different blocks, G, T, A, S, C. That is again the middle ocean ridge basalt that's plotting here. And all these different plots, we have to use the key from the things before. A, that is then probably again from Amsterdam. C, that is probably then again from the Comores. I, that is Iceland, and so on, yeah. That is from different locations, yeah, where our data are plotting, and then we can compare these ratios again with our middle ocean ridges, with our enriched mantle, and with our South St. Helena component, yeah. There again the same, we have the 206 lead to 204 lead plotting against 104, 43 neodymium to 144 neodymium with all the different locations inside. Then here the addition of sediments, yeah. And here in grayish again the middle ocean ridges. So, and all these blocks representing then the different locations from the places where they have studied the rocks. So, and I mean, the thing what you should have in mind from this class, that is just that you are using different isotopic systems, radiogenic isotopes, stable isotopes, to get the fingerprint from your basalt or your igneous rocks which you are studying, so and to figure out where they are coming from. Yeah, nobody is now from a fourth-year student expecting that you know all the fingerprints from all these islands where they are lying in the strontium and neodymium isotope diagram. But you should know that the strontium and neodymium isotope diagram can be used for classifying the different rock types, and I mean that you have more primitive rock types, more enriched rock types, you have the toliitic rock types which are subalkali, you have alkalic rock types, you have calc-alkaline basalts or rock types, and then you can use this isotopic system to distinguish them from each other. So, and here, for example, they have used the helium-3 to helium-4 ratios from the atmosphere against the 87 strontium to 86. Then you are going here into the primordial mantle. Here you have the Hawaii, yeah. Then in stippled line the Iceland, then we have here the Middle Ocean Ridge, and here the Tristan da Cunha, and here you are going now close to the sediments, yeah? And that is then important to figure out, or the use of all these different isotopes, to figure out the geotectonic history from your rock samples. So then we have here a model, yeah, we have this a dent in the, a dent in the oceanic crust because of the overload of weight here where we are forming in the oceanic islands, yeah. So we have here the lithosphere, and the lithosphere, that is variable depleted warp source mantle, yeah. So, and there we have the depth of the magma segregation. Here we have the zone of partial melting, yeah. Here the depth in hundreds of kilometers, we are just going down 200 kilometers. So, and here that is the boundary between the lithosphere and the asthenosphere mantle. And there we have, over this span, we have the more zone of partial melting, and then we can bring recycled ancient subducted oceanic crust from seawater alterated morb and oceanic sediments. We can bring it in from the old subducted oceanic crust. Therefore, it would now important to do the oxygen isotopes, yeah? Because if it is seawater alterated oceanic crust, then you can identify this with the oxygen isotopes, which I'm doing in my own studies. So, and then you have this component from the recycled ancient oceanic crust. Then we have an enriched plum component, yeah, which is internally very heterogeneous due to the migration of small volume of partial melts over the last 4.5 billion years ago. This will then all rise up, and then you are forming your ocean island basalts above, which is enriched in the trace elements, in the incompatible elements, yes, shows another isotopic values compared to the morb, yeah. So, and this is because we have here this enriched plum component inside, yeah, that's the reason for this, yeah. And that you should have then in mind, and there you should be able to write this down. So then we have here another nice diagram from the Hawaiian basalts to show the change in isotopic composition between the Toleitic shield building stage and the post-erosional alkali stage. Yeah, then I'm right. At first you are forming the Toleitic stage, that is when your volcano pops out of the water, and then later on you have the post-erosional alkali stage. Yeah, here we have for again 87 strontium to 86 strontium. Here 143 neodymium to 144 neodymium. So, and here we have the koala, the bulk earth in this corner. Then we have here the Hawaiian field in stippled line. We have here koala Toleitic shield that is here. So then we have here the Toleitic shield. That is the shield stage when your volcano pops up of the water. So the first melt which came up to the surface to build up the volcano, that is of Toleitic composition. And later on we have the volcanic post-erosional series, and then we have the alkali capping phase, yeah, and we have the post-erosionally alkali phase, and therefore we have now as an example Honolulu, and I was supposed to go to Honolulu this summer for a conference, but the conference is now also postponed because of the virus, and I have to give my presentation then online. So here we have now a model showing the evolution of the Hawaiian island. Here we have the rise up from plumes from the asthenosphere, and the lithospheric mantle is moving, the lithospheric crust or the oceanic crust is moving to this side, and therefore we are forming now a Toleitic volcanic rocks, yeah? We are forming them at first. So if we are now looking at the youngest volcanic rocks at the Hawaiian island, then the youngest volcanic rocks, they are Toleitic in composition, and the old ones are alkalic, yeah? So then we have the volcanic and plutonic rocks of the oceanic island crust that we have here, yeah? We are forming a Toleitic rock, and here you have then the high-level magma storage reservoir here in dark, in the black. Then we have the oceanic crustal layer, and this is of morph composition. Then we have the depleted astenospheric source of N-type morph, that is here in white. Then we have the depleted N-type source mantle depleted by magma extraction of the middle ocean crest, a middle ocean ridge crest, that is then here in dotted line. So, and here the two plums are coming with the enriched plum component from the mantle, and that was fed by these old fragments of ocean of subducted or remnants of slabs hanging around in the boundary of 670 kilometer and breaking in periodically into the lower mantle. So then while the crust is moving away apart, then we have here still some melt left here beneath. So when this later melt is more fractionated, then we have a more potassium-rich melt, and then we are forming then later on a more alkalic, or we are forming more alkalic basalts, because we are having a more and highly fractionated melt. And their partial melting processes will also take place. Yeah, we do not have here longer storage of magma. We have here the eruption of partial melting will take place here, and that will cause another change in chemistry of our investigated Hawaiian rock samples. So that was it for today, for chapter 9. Have a lot of fun with it.